Hello, my name is Bill Kiker, Kilo Charlie 1 Hotel Tango Tango, and today I'd like to talk about how to build and operate a QRP Earth Moon Earth radio station. So the outline of my talk is shown here. First, we'll talk about what are we trying to achieve here. I'm going to tell you about QRP EME. What is QRP EME, and who can I contact? Then we'll describe building a QRP station, a low power station, including the components and the cost. Then finally, I'll talk about EME operations, which include preparations for a QSO and then operating JT-65B during a QSO. Then I'll show you a QSL and then end the talk. So what we have here is a graphic that illustrates exactly what amateur radio Earth Moon Earth or EME communications are. It involves sending a signal from the Earth up to the Moon, reflecting off the surface of the Moon, and having that signal travel back after a 2.5 second delay to the Earth, where someone with the appropriate transceiver and antenna can receive that signal. And you can develop a QSO from that using digital communications. So what is QRP EME? Well, QRP means low power operation. That's operating with as little power as possible. And QRP EME extends that, meaning that you're transmitting minimum power with a single polarization and minimum antenna gain in a specified band. We're going to be looking at 2 meters. So the way to basically wrap that together is to talk about the product of the power times the aperture, where each of those is expressed in decibels. So you have a product of power times aperture, which is equivalent to the effective isotropically radiated power from the antenna. So that will be a figure of merit for our station, and you'll be able to compare that to the larger stations. In this particular case, you will only be able to communicate via the Moon a QRO station, which is a high power station with more than one antenna and most likely more than one polarization. So we're going to talk about QRP EME. So the first question is, what band should I operate in? Well, I've chosen 2 meters, 144 megahertz, basically because most EME operators work there, and the equipment is available and reasonably priced, and the tolerances and losses in the cables are less at 2 meters than at higher frequencies. So what kind of antenna is required? A Yagi antenna, typically 9 or more elements with a gain of about 14 dB or more at 144 megahertz. So we have to mount this antenna on something. What kind of a mount would you use? Well, you don't need a tracking mount. You only need a tripod and some means for attaching this antenna to the tripod. You can point the antenna by using a compass and an inclinometer. Point it by hand, and you'll see why. How much power is required? Well, QRP system requires between 100 and 200 watts. That particular power level will give you operations roughly half the time. And then finally, you'll need a low noise amplifier, preamplifier ahead of your receiver to amplify the extremely weak signals from the Moon. So we've chosen a Yagi antenna. Should we mount it horizontally or vertically? Well, I've done some calculations using Easy NEC software, and the horizontally mounted antenna outperforms the vertically mounted antenna by around 3 dB. So you'll use a horizontally mounted or horizontally polarized antenna for maximum antenna gain. This is what that type of an antenna looks like, and it's on a metal tripod with a PVC plastic mount, and I can rotate that in azimuth and elevation. Okay, well, this is now a block diagram of the entire system to show you what components, major components, are required. I've also listed the cables and the noise figures, the power supplies, and you can see the color coding associated with the power supplies: red, the RF being blue, and the RF power is being listed as green. So you can see the heart of it is the ICOM IC9700. I used an ICOM IC9100, which is a bit more expensive but unavailable now. So you need a transmitter that works in the VHF for long duty cycle waveforms, data waveforms, like FT8. Ahead of that is a relay, which is an RF Vox relay. That means it switches on and off in the presence of RF power. In this case, the maximum power it can withstand is 25 watts, so you have to make sure by measuring how much power is coming out of that transceiver. So it's less than 25 watts, preferably about 10 to 12 watts. There's some loss associated with it, so it then goes into a power amplifier, where roughly 10 watts brings it up to 200 watts, long duty cycle. Not all amplifiers are long duty cycle. These waveforms, JT65 waveforms, EME waveforms, have a very long duty cycle. They run for minutes at a time. And then we have the antenna radiating about 177 watts into about a 38-degree beam width. So this is a picture of the ICOM transmitter, and you can see it's dual band, very nice transceiver. I don't own one myself. The 9100 preceded it, and it has about essentially the same noise figure when the internal preamplifier is on. So you need to turn that on. That's why it's highlighted in red. And you can see you can adjust the transmitter power from a half watt to 100 watts at 144 megahertz. This is another key component. It's a preamplifier that operates on the RF power. The presence of RF power at the input bypasses the amplifier using relays, so it protects it as long as the power, maximum RF power at the output is less than 25 watts. And this is why you need an amplifier to follow this. So by putting this preamp here at this point, it's unusual, but it doesn't require any type of switching or coordination because all that's done internally with the Vox switch. So it is a very good noise figure, about a half dB, and the bandwidth is sufficient to support this communications. My original design didn't have this. It had a version of this, but it was good to 160 watts. But I still mounted it in the same location. This is a less expensive alternative, and they may not actually sell the one I had. So then we go into the power amplifier to recover the power. Remember, we're down to about 10 watts out of the preamplifier. And so we need to bring it up to about 200 watts, 100 to 200 watts. And this particular amplifier that's fan-cooled can run long duty cycle. I've used this successfully many times. It needs its own power supply, and the input power should be limited to less than 20 watts for all modes. This is the transfer curve for that amplifier. You can see how the output power follows from the input power, and we're running about 10 watts or so. So you can see it's over 150 watts in this particular case. So now we're going to talk about the cost of the system. And so I've got a spreadsheet here that lists the cost of all the major components. And you may have some of these already. For example, I didn't bother listing a personal computer. You need a personal computer running Windows 10 or 11. You don't need the software. You certainly need the software for JT65B, but you don't need antenna modeling software, even though that's free. So once again, the transceiver is about $1,800. The power amplifier is about $730, and then the antenna is about $350, although you may be able to get it cheaper if you purchase it directly from M2 Incorporated. You also need power meters. Remember, you have to check to see what power levels are present at the preamplifier and following that. And the rest are basically components you may have around and choose to use. There's also the tripod located there on the bottom of the list. So the total is about $4,300 to build a low power EME station. These are 2023 prices. So I have a station like that. that's marginally minor, in a minor way different, but has all of the primary elements, the same antenna, and a similar receiver with the same noise figure, and essentially the same preamplifier with the same noise figure. So these are the values. Notice that the power aperture product is less than 40 dBIW. That's a number to remember because we're going to compare that to the high power stations. The safe distance from this is about 25 meters from the main lobe and about 6 meters from the side lobe. So, and the other thing you should remember is that it's very difficult to put RF power along the ground. So this being only 2 meters above the ground, and it's pointed close to being horizontal or 10 degrees, 15 degrees, you're not going to create much of a problem beyond 100 feet. So in order to operate the station, you have to prepare for the QSO. You can't just turn it on. You have to know when and where the moon is going to be. And the best time to operate is at moonrise or moonset because you have the ground gain associated with the horizontal polarization. You get another 3 dB, so that's very important. So choose moonrise or moonset, and then that'll determine when and where you can point your antenna. You have to look around your station and see where you have clearance for a relatively low angle. And so you look for buildings and trees. So to help plan for that QSO, you can download MoonSched software, and the URLs are listed for the key software here. You'll see how I use that in later charts. You'll need JT65B, which is in the same package that FT8 is in WSJT-X software. And you'll have to set up your radio the same way that you set up for FT8. In this case, a USB link between the radio and the computer, and you can go online to see how to do that for your specific radio. One important factor is you need this so-called call3 text file for JT65B to work properly. You gain 4 dB if you have that file present. So to do that, you have to register your station information in the call3 text database at that URL listed in blue. And then you take the resulting version of the call3 text and put that in your WSJT-X computer folder. JT65B will refer to that when it's decoding messages. So then how do you make a contact? Well, you can go to this particular website, the WSJT-1 EME website for 2 meters only and EME only, and that'll tell you who's operating. A lot of people will list their frequencies and their call signs and say, I'll be operating at this point in time at this frequency. You can also list yourself. You can also announce to the world that you're going to be operating. That'll help others know what your frequency is so they can find you and do the contact. And so then as the charts move on, we'll show you what a successful QSO looks like. So again, I said the best time to operate is during the first hour after moonrise, and I've done that, and then during the hour before moonset. So the moon is up, but it's close to the Earth, just less than 20 or 30 degrees from the surface of the Earth, the horizon. So this will set the antenna azimuth and elevation angles to point to the moon. But you have to know when that's going to occur, so that's why you need that MoonSched software to tell you where the moon will be at a given time. It also provides other information about noise sources like the sun and the Milky Way, which you don't want in your beam width. That'll raise the noise figure of your receiver. So, as I said, the antenna operating azimuth and elevation, in my case about 38 degrees, 38, 35 degrees, something like that. That tells you where the beam is going to go, and you can see if it's going to clear buildings or not. And then finally position your antenna only one wavelength above the ground. That's all you need. Makes it easy to point by hand and to service the antenna. So in my case, this is the geography I have. You can see my home in the center here, and the antenna is pointing out to roughly to the northeast at the right where the rising moon was on January 19th. And you can see that I'm pointing between a house and some trees. And the distance of that house is greater than 100 feet. There's no problem with illuminating people in the house with your RF energy. Because I'm in a development like this, I have to set up the antenna and break down the antenna each time I operate. I have to move it back into the garage. So that's another reason why I have an antenna that's only roughly 14 and a half feet. I have to be able to store it on the wall in the garage. I mentioned that the MoonSCED software does predictions, and these are the predictions for January 19th, 2019. You can see it shows you the optimum times to operate. In this case, you can see the 22nd of January would have been the optimum for the entire month of January, but because of the constraints of buildings in azimuth and trees in azimuth and the elevation angle, I operated on the 19th. So typically I have a window from the 18th, 19th, and 20th. So I got it working on the 19th. And this is again output from that MoonSCED software. You can see the predictions are encircled by the ellipses, maximum elevation 28 degrees. It calculates then what time you can operate, UTC, for a given azimuth and elevation. And that met the requirements that I had for the limitations I had at my system. This is a different type of plot. It shows that the window was roughly ranging from 2030 to 2200. So that's about an hour and a half or so that I had to operate. The moon moves at 10 to 15 degrees per hour. So you can see that with a beam width of 38 degrees, even 30 degrees, it's not going to move out of that beam width very quickly. So you can point it once and you can operate. Then if there's a break between QSOs, you can move it slightly to accommodate the position of the moon. So a 2-meter QSO, EME QSO, looks like this. This is my first QSO. It's with a Russian station, Romeo X-ray 1 Alpha Sierra. And you can see it's listed here. The times are listed as it goes down there. The time started 1 second after the UTC minute. And it's important to notice that west transmits on odd minutes and east transmits on even minutes. So you have to set your system up. So if you're looking at the rising moon, you're moving, looking to the east. So you are on the west, you transmit on odd minutes. This is what the QSO looks like in detail. And you can see here the red line, just like FT8, indicates that a signal is being received and he's transmitting back to you. So you click on that with the mouse. And in fact, it's important to notice that JT65B doesn't have auto sequence. The operator must click on each received message to get to the next position in the QSO. Very important. You can see the red messages are the ones from the Russian station. RO, or Romeo Oscar, is a tone sent after the long message that he sent. And then 73 is farewell. So that's what it looks like. Another view, another screenshot is shown here, where below I've brought down the actual transmissions, both mine and his transmission, and the signal to noise ratios, which are reported. You can see he's receiving my signal at a minus 24 dB SNR. I received his at minus 18. That was highly unusual. It was very strong for me. He has a stronger transmitter than I do, and he has adaptive polarization, as you'll see, which corrects for the rotation of the polarization, my polarization towards his antenna. So he can receive any polarization, is what I'm saying. I can only receive horizontal, so I was lucky to get minus 18 dB. Very important. And you can also see the round-trip travel time, which in this case for the range involved was 2.4 seconds. There was a 0.2 of a second error. That's relatively small. That's a collective error between my machine and his machine. I mentioned that there's a bulletin board that you set up calls and you can then evaluate the received call. This is what it looks like, and I've highlighted in yellow because it's difficult to read otherwise, the messages to me on that particular night. You can see there's a call, and then later on there's a acknowledgement where he lists what his system is. Signal to noise ratio is minus 24 dB, and he's got a 4 times 15 cross polarized antenna running at about a kilowatt. So this is a very important site because it helps you see who's operating, and it lets you tell people that you're operating. You see the website down below. This is Romeo X-Ray Alpha Sierra's system. You can see the radio has an antenna that has 4 Yagis where they're cross-polarized elements. You can see them forming the letter X, X-ray, and they're receiving both polarizations. He has an adaptive receiver that utilizes MAP65 software to combine the signal from both of those antenna arrays into one signal. That overcomes losses caused by Faraday rotation in the ionosphere. So it's optimized. Also notice his antenna gain and power aperture product, 53.5 dB. That's more than 20 times stronger than what I've got operating. So that's the kind of station you communicate with. There are a lot of stations like that. They're looking for you because it's no problem for them to communicate with each other, and they've done it already. What they're looking for are the small QRP stations with novel QSL cards, call signs, and Maidenhead locators. This is a Romeo X-Ray 1 Alpha Sierra's QSL card from Russia. You can see his antenna outlined against the moon. Again, cross-poled 4 elements. I've listed his power aperture product again, very, very high power. And you can see that the reverse side of the QSL card is shown. And you can see under RST, it says quotations O, Oscar. Oscar means I've received your signal with sufficient signal to noise ratio. Generally, they don't write in the signal to noise ratio. Everyone writes O at the end of a successful QSO in a QSL card. So that's one of the characteristics that operators use. So in summary, I've described how to build and operate a QRP Earth-Moon-Earth radio station. So to do that, I've described the system components, showed you a block diagram, and listed the parts and their cost so that you could potentially go out and purchase the equipment and put it together. You have to be careful though. Remember that preamplifier is power sensitive and you don't want to overdrive your final amplifier. So you need a power meter, a useful, reliable power meter that I've listed, something like that can reliably measure the power at 144 megahertz so you don't damage things. So then I've described a successful QRP EME QSO utilizing JT65B software. And with that system, very similar to the one I'm describing now with its updated components, I've been able to operate successfully and contact 6 big gun stations, 6 big gun or QRO stations in Russia, Slovenia, Italy, Netherlands, England, and Spain, all looking to the east because I'm working with the rising moon. So finally, the lessons that I've learned basically indicate that you need for a minimum 144 megahertz EME station, the equivalent isotropic radiated power aperture product has to be on the order of 40 dBIW. And that's a combination of antenna gain and transmit power, 100 to 200 watts, antenna gain of 14 dB, and operating low so you gain another 3 dB in performance from the ground gain. So therefore it's best to operate at low elevation angles during moonrise or moonset. So that's pretty much the presentation I have made for you today. And now I'd like to be able to take questions and hopefully provide some answers for this particular session. Thank you. Okay, hopefully you can hear me now.
Yeah, I can hear you. Go ahead, Bill.
Okay, good. All right, so I've got a poll that I prepared that you can answer during this period of time. We have quite a bit of time now in this session. I'll launch that. Let's see. If we get to it. Okay, well. Well, I don't want to create a new poll, but I do want to launch this. So the basic idea of the poll is how many people have actually done EME? How many people would like to do EME? And how many have unsuccessfully done EME? There are only about 7,000 hams in the world that have actually registered on the site that has the list of all the hams. You know, I forget the name of it, but in any case, there are only about 7,000 people. And earlier, when this presentation, whenever this conference started, we learned that there are about 700,000 licensed hams in the U.S. alone. So we're talking about a very small percentage of people that have actually tried this and done it. Not all the 7,000 have actually done it successfully. That's an important point too. So this is probably the most difficult thing you can attempt to do as a ham. I see that the poll looks like it's active now. So you can answer those questions if you want. There are a choice of 3. And if you have any other questions, let's see, there are some questions here.
Yep, we got some questions.
Okay, Kevin, could you read them to me, please?
Yeah, Dan asked, will the slides be available for download? If I remember right, like last year, this presentation is available for 30 days after the QSO today, so you could review the whole presentation.
I'm going to interrupt. This is Eric from the backstage. All the collateral material for all the presentations, if it was submitted, is on the QSO Today hamexpo.com website under presentations. So if you go to the presentation, you'll actually see all the collateral there now.
Thanks, Eric. Okay, another question we have. Do sun flares affect the bounce, and is it atmospheric lensing that it helps to boost the signal?
The most significant atmospheric or propagation factor when you're doing EME is the ionosphere. The ionosphere does not reflect the 2-meter signal, but what it does do is Faraday rotation. The Earth has a magnetic field and it changes across the Earth's surface. There's also the electrons surrounding the Earth in the ionosphere. Those two interact with your radio signal to rotate the polarization. The idea is it's a totally random rotation. At 2 meters, the total rotation might be as many as 5 times. That is 5 times 360 degrees. There's another factor too, I'll just mention, that also affects the polarization. That's where you're located and where the other guy is located. There's going to be a rotation just associated with the fact that you're in one location, you're in a different location on the Earth, the other guy's in a different location on the Earth, and the moon is moving. So that will give you a rotation also. So the combined effect is to look at it as if it were a uniformly distributed random variable. The best analogy I can think of is a roulette wheel. Think of a roulette wheel that's spinning. The pit boss throws the ball onto the roulette wheel, and it rotates and rotates and rotates. Where it stops should be totally unknown, a random variable. So that's what happens to the polarization, because you don't know who you're going to talk to. That's one factor, the geometric factor. And then we don't know what the ionosphere is doing. If there's a solar flare, the ionosphere is going to be more active and actually rotate even your signal even more than what it would have if it were quiet. If you're operating in the daytime, if you're operating at night, these are all different ionospheric conditions that will change the rotation, the position of your polarization. It'll rotate it as if it were a random variable. That's what kills EME for the little guy. The QRP stations cannot adjust their polarization very easily. That's why I listed single polarization. Horizontal polarization is all that I use. The big guys have enough equipment to use both polarizations that they can sum up in a vector sense, so they get the entire signal. That's why I was totally surprised to see that I only had a negative 18 dB SNR whenever I talked to the Russian station. The conditions must have been near ideal. I can calculate what the signal to noise ratio is, and that's about the best you can do. Typically, though, what you could expect is roughly a 3 dB loss because of a polarization mismatch. But the polarization could be totally orthogonal to your polarization, in which case you might have a 20 dB loss, and it's going to be random. So it can range from roughly 0 to 20 dB, with the median value being 3 dB loss. So that's why it's difficult. I operated for 6 months and I got 6 QSOs, successful QSOs. And because it was further limited by when I could operate, it had to be, the moon had to be rising between the neighbor's house and the trees. There were very specific days that I could operate. So it either worked or it didn't work. And so that's something you have to take into account. That's why I said that roughly half the time it's not going to work. But if you want to get that ultimate QSO, that's almost 500,000 miles away. A QSO that's receiving signals that are, well, I'll tell you, you've heard of watts and milliwatts, microwatts, picowatts, nanowatts, attowatts, zeptowatts. You're dealing with hundreds of zeptowatts, which is an incredibly small signal. And it's because you have error correction coding in the JT65B waveform, and you have this deep search algorithm that looks at the 7,000 people who are operating and uses that information to help decide or decode what the message is. It's for Romeo X-ray 1 Alpha Sierra or Kilo Charlie 1 Hotel Tango Tango. That's why you have to put your name and your call sign into that database. So that's why I listed it. Very important. So the ionosphere is the big killer in this case. And at HF, it allows you to communicate to Australia, even at 10 meters. When you're going to the moon, it's going to rotate your polarization, and you don't know what the result will be. You'll be lucky if you can communicate with only 100 watts and one polarization and one antenna that's close to the, looking pretty close to the ground, horizontal, to get the extra antenna gain. So next question.
Okay, yeah, Bruce, VE9 Quebec Romeo, does the amplifier need to be linear?
Okay, well, whenever you think of nonlinear amplifiers, there might be some distortion, and you might get harmonics that are generated that would be undesirable unless there are filters at the output of the amplifier. If you looked at the transfer curve that I have in my talk, you can see that I'm operating in a slightly nonlinear region, and I don't think that created a problem either with the FCC or in transmitting the signal. So the answer is, it's not as important as you might think, but I didn't want to overdrive the amplifier greatly. But you can see I was on pretty much where it started to go nonlinear.
Okay, next question from Stephen. Kilowatt Sam in 1 George. The ARR no longer makes preamps. What do you recommend? Also, opinion of an amplifier with built-in preamps?
Okay, well, I'll answer the second part first. There is a power amplifier, a high power amplifier that has a built-in preamplifier that I'm aware of, the Mirage. It's sold by MFJ. I think it's one of their divisions or something. But the problem with that, and I would have put that into the talk, but the problem with that is that I'm not sure if it's it can handle long duration waveforms. If you read the fine print, it sounds like it may not be able to do it. What I'm suggesting is the amplifier that I use, because I know it works. All right, now get back to the preamplifier, ARR. Now, I went to the website to see what the current cost was because I built my system in 2019, 2018. And it turns out that I didn't see my preamplifier listed. On the other hand, I noticed the preamplifier that's in this talk, that's listed in the talk. It has the ARR designation, and there's a price associated with it. I did not call ARR to see if they were willing to sell that or if they still made it. The difference is they're both Vox operated preamps. In other words, the presence of RF switches the preamp out, protects it. The difference between the one I have and the one that I think they're still selling is mine was 160 watt input, although I ran it at 10 watts. And the one that I saw listed that looks like it's for sale has a 25 watt power limit. So that should still work with this system that I've shown. So I think they still do, but it would require a phone call. Give them a call, give them the number that's on the chart and see if they still sell it. I didn't do that.
Okay, next question from Gerald. Kilo 8 George, November George. Why operate with the moon near the horizon?
Okay, well, there is this idea of ground gain. The best way to explain it is if you took a mirror, take a mirror and place a pencil on the mirror, you'll see an image of the mirror, an image of the pencil in the mirror. It looks like it's twice as long. This is why a 1/8 wavelength antenna, vertical antenna, looks like, a quarter wave antenna looks like a half wave antenna because of the image response associated with the antenna being close to the ground. The same thing is happening here. We're putting the antenna horizontally, and there's an image of the antenna. I said it was up 2 meters. There's an image 2 meters below the earth that looks like there are two antennas in a vertically arranged array. That's where the extra gain comes in. Remember I said it was about 3 dB? Well, that was in a model. I don't know exactly what it was because NEC has different models for the ground, conductivity and dielectric constant. But that's what it showed. And the most important thing is that it shows that the horizontal polarization is better than vertical polarization in this case. And so that's why I operate near the ground, is to get the extra gain. There was one QSO that I did with the biggest station that I know about. It was India, I think India 2 Foxtrot Alpha Kilo. It's an Italian station. He has like 16 Yagis. It's an incredible system. You know, he might have like 57, 58 dB IW as a power aperture product. So I thought, okay, he wanted to contact me. He wanted my QSO card, I suppose. So we set up we scheduled a QSO. And for him, it was later in the day. So I actually had to point my antenna upward beyond where there would be any ground gain. And it barely worked. He wound up transmitting vertical and horizontal alternately so I could receive the signal. That was to mitigate the effect of the ionospheric polarization rotation on my receiver antenna. So, you know, that's the experience I had with operating beyond the horizontal or close to the horizontal. And that was the most difficult QSO that I had done with the most powerful station that I know about. I have to admit, I don't know all the stations, but that was a pretty good station that Italian ham had.
Okay, next question from Martin, November 5, India Yankee. Do you have any EME contacts since 2019?
No, the objective was initially to build a station that would operate on the 50th anniversary of the Apollo 11 landing on the moon, 1969, 2019. So I started in 2018. My first QSO was in January, and the last one was in May. After that point, I had problems with the receiver. And it could have been, well, the fact is the 9100 receiver provides 12 volt signal, a 12 volt power to the preamplifier through the cable. And it may not have been working. I checked it after the fact, and I didn't see any voltage, and I haven't tried to troubleshoot that issue. That could be fixed. It could be remedied by having an external power supply or a power supply separate from the radio, and then going in via a connection through the coax that passes RF and passes the DC signal towards the preamplifier. So I built one of those circuits, but I didn't try it out. And I haven't operated EME yet. On the other hand, what I have done is I've put together presentations like this one, and there are 3 presentations that I've given, and they're all on YouTube. One is an hour long, and the other 2 were given to 2 clubs in Zoom meetings. They're an hour and a half long. There's much more information in it. It's not a beginner talk. It talks about the physics of the ionosphere and so on. So you can search YouTube with my call sign, or you can look up, I have a YouTube channel where I put these videos on. I have another one I have to load. I haven't done it yet, but that'll give you more of an explanation. That's how I've been spending my time, trying to understand how JT65B works. And those talks will tell you exactly what the waveforms are, how they switch, the 64 FSK waveform, how many bits are transmitted by every tone. I think they're pretty good presentations, and there were comparable sized audiences at the 3 different clubs that I talked to. So check out YouTube for more information. Am I going to get back on the air? I would like to, and I may. Remember, I have to set up every day that I do this. I can only do it for a few days every month. So it's a matter of preparing, finding out when, and then see if that I can fit it into a schedule that I have.
Okay, next question comes from Al. Whiskey 7 Sierra Yankee Kilo. More power or better antenna? I'm guessing, as all other modes, a better antenna will help with both receiving and transmitting?
That is correct. The antenna is the key. You can spend a lot of money on a kilowatt amplifier, and I know people have, and I think it's more typical than not, but it's not going to allow you to receive the signal. Remember, the big stations have huge antennas and a lot of power, and there's still a problem with hearing them. There are a couple of solutions. One is to have 2 antennas, the same polarization, so you gain 3 dB. That helps. But on the other hand, and people have done this, I know hams that have done this, you get a vertical and a horizontal antenna. And you saw the Russian station had a dual polarization antenna where the antennas were like the letter X, X-ray. They take the signal from both of those, they can combine them. And if you look, you can get an SDR play dual receiver. And you could potentially take those 2 signals and it will do the mathematical operation that adds the 2 vectors. So you get the V and H component, which pretty much is everything. You lose a little bit in noise because you have a dual receiver. But the point is that people have done that. They've used SDR receivers with dual channels, and it's the SDR play duo, SDR receiver. The other thing you can do is you can take, like the Italian ham did, you could take a V and an H, and this is where I'm closest to doing, a V and an H antenna separated by about 10 feet. You need about 10 feet so that the VSWR isn't affected by another antenna like this or like this. 10 feet apart, orthogonal polarizations, and actually they probably would be best like this. And so what you can do then is you could switch. When you're trying to receive, you could switch and see which polarization is working the best. There will be a difference, and I know that there is a difference because I've talked to hams and they've done that. Transmitting is a little more tricky. I don't think you'd want to do that. Transmitting, you might wind up with a problem. And remember, the other guy at the other end has got adaptive polarization, so you can transmit. He'll receive the right polarization after the ionosphere has rotated it.
Okay, next question is from Gary, November 2, Alpha Mary Charlie. Does the NF of the ICOM preamp overwhelm the 0.5 dB of the ARA preamp?
No. The thing that's creating the biggest issue with the noise figure is I have the preamp behind the power amplifier, the linear amplifier, and behind the cable. And that's because I didn't want to put in a sequencer which switches it in and out. And that's why I have a box operated preamplifier. So you can do the calculations and see if you just forget about what's in front of the preamp, but you can see that the preamplifier signal is amplified. It's amplified about 20 dB. So that's well above the receiver noise that follows it. And in fact, you can find websites where people have models for EME receivers, and you can plug in the different numbers and it'll automatically calculate for you what the noise figure is. But the noise figure is determined by the cabling in front, the loss in the power amplifier, and then the noise figure of the preamplifier, and not the noise figure of, to any extent, the noise figure of the 9100 or 9700.
Okay, one more question from Seth, November 3 X-ray. So you mentioned that you went with 2 meters because most EME stations are there, and it was lower feed line loss. Would there be a potential advantage to using a shorter wavelength?
Okay, there are some interesting facts that I couldn't talk about in the limited time here, but they are on the YouTube videos. One is how does the rotation of the polarization depend on frequency? Well, it turns out the higher the frequency, the less rotation you have of your signal. And in fact, the guys that are operating in the microwave region, say X band or 10 gigahertz, they use circular polarization. And circular polarization is not affected by the ionosphere. It's not affected by the orientation of the antenna. What it is affected by is a circular polarized signal reflects off the moon, and say right hand is what the convention is. Right hand out, it bounces off the moon, and it comes back left hand circular polarized. But there are feeds, antenna feeds for parabolas that have right hand out, left hand back. So the hams that operate at the microwave frequencies have feeds, they're waveguide feeds that feed right hand into the parabola and receive left hand out of the parabola back from the other guy. And that pretty much eliminates the effect of the ionosphere. There are other issues though. Remember in the very first talk, they talked about the losses in coaxial cables. Well, you're not going to use a coaxial cable at X band. You're going to have to bring a signal up and maybe use a multiplier effectively or a transverter to get the signal at X band. And the new ICOM transceiver, I think it's the 908 or something like that. If you look, it operates up to X band, up to 10 gigahertz. It works at roughly with gigahertz, 2.5 gigahertz, 5 gigahertz, 10 gigahertz. The part that generates the signal and receives the signal is right at the antenna or driving waveguide at the antenna. So that's another piece of equipment. It's generally more costly to operate. And there's one other factor for me, especially in operating at roughly 440 megahertz. The issue is there's a radar on Cape Cod called PAVE-PAWS. It's used for ballistic missile defense. It operates in the UHF, and they don't want people operating with a high gain, power gain product nearby. One of the interesting things that happened was even at 144 megahertz, the first time I operated was in November 2018, and I didn't know anything about when I should transmit. That's why I put that information in. I didn't know about the list of hams. I just started transmitting. And it was interesting. I heard a ham in Rhode Island. And I thought, oh, I'm getting a signal from the moon. It was a direct path from Rhode Island. And I looked at it much later, that is this year, looked at the signal I recorded. And that, by the way, is also in the YouTube videos. And you could see a reflection of the signal from an airplane that was somewhere in his main beam, and I was in, and the airplane was in my main beam. We were both pointing to the east. So the signal that I got from him was coming in coming from his side lobes into my main lobe. Then I got a return from an airplane. You could see the airplane had a Doppler shift as it finally left the beam. And it's interesting, you're able to, in the YouTube video, you can hear the sounds of JT65B, the 64 tones that represent the digital message. So I hope that answers the question. So one other comment, I have a chart in my YouTube videos that introduces frequency shift keying. So if you remember the movie Close Encounters of the Third Kind, and the mothership is landed in wherever it's landed, and there are a bunch of engineers and scientists there waiting to communicate, and all of a sudden you hear these audio tones coming from the mothership. And they even show the tones almost like a spectrogram in the movie. That's frequency shift keying. So take a look at that scene in the movie. It's interesting. That's frequency shift keying. It illustrates you're transmitting multiple bits in a given tone, and you use an alphabet of tones. In the case of FSK 64, it's 64 different tones. 64 tones can transmit 6 bits per tone. So that's one of the interesting things associated with either FSK 8 or FSK 65 or even 66. 65 would be a tone that's used for synchronization. And you'd have 64 bits, 64 tones, which is 2 to the 6th power. Any more questions?
I have to unmute myself here first. Yeah, I have a couple questions myself.
Okay.
Antenna heights. I live in Montana and we have nothing but hundreds of trees around our house. So I'm thinking about putting up a tower with using a azimuth horizontal rotor at the top with some stacked arrow antennas. Is antenna height really crucial, or would that work be fine just because of trees?
Yeah, the ham that I contacted in Rhode Island, the first one, he's got a setup where he built a tower, relatively small one, out of, I think, 2x4s. And he's been very, very successful. I think he's running 2 antennas right now, and then he's also worked up at X-band, 10 gigahertz. So the tower doesn't hurt. It's just going to be a different antenna pattern. You're still, if you're running horizontal polarization, there's still going to be an image of your antenna. It's going to be further away, so it's going to change the antenna pattern. I don't know what that is. I'd suggest, trying out easy NEC. That's about the best thing that amateurs have to use right now to calculate antenna patterns. But I think there would be ground gain. The antenna would probably be pointed, the main beam would probably be pointed closer to the ground. The main beam in mine was pointing around 15 degrees above the horizon whenever I was working 1 meter away. The other advantage I have is I have a very simple system. I point by hand. That means I have to move the antenna. And so I use a tripod. And that's worked. So the theme here was to see what could you do with a minimalist approach. 1 antenna, 1 polarization, no tower, 100 to 200 watts.
That was my other question. I've read someplace where they're doing a contest for QRP Earth to Moon with people trying with 10 watts or less. Have you heard anything about that?
No, I haven't, but what frequency is what I would ask, because I remember there's an antenna involved, and the guys at the higher frequencies, they don't use Yagis. You don't use Yagis after about 1 gigahertz. You use dishes. Mm-hmm. And people have used dishes that are associated with, remember the old dishes that they had for the S-band, 2.5 gigahertz TV satellites. Some people have adapted those and use them at X-band. But it's even more complicated than that, because there is a physical area associated with any antenna, whether it's a wire antenna, a parabola, or a Yagi, or anything. There's an area, a collecting area. If you're looking at a receiver, there's a collecting area. And so it's related to the wavelength, and it's related to the dimensions of the critical dimension in the antenna. Obviously, a dipole is pretty easy to describe, but a dipole at 10 megahertz has a larger area than a dipole at 20 megahertz. The area is related to the physical length of the antenna. In the case of a parabola, it's easy to calculate because you can measure. You can calculate the cross-sectional area of a parabola. And that's the capture area for an antenna, but it's more difficult. Actually, there's an equation, not that difficult. You can calculate the area for a dipole. You can calculate the area for a Yagi. If you know the gain, you can calculate the area. The two are interrelated. So high frequencies, typically high gain. And it doesn't look, hey, look, I got a gain of, 25 dB. But it depends on the frequency. And the frequency will tell you how big, physically big that antenna is. And so an antenna at 144 megahertz that's a parabola is going to have to be pretty big to work. That's why I used a Yagi.
Yeah, I was going to say that's what I'm looking at is using a dual polarized antenna from Arrow, so you can do both, and it's at 2 mega in the 2 meter band area. So
yeah, I've used the Arrow antennas for satellites. And the gain might be a little bit too low for this, unless you can, well, you still have to receive on that antenna. That might be a little marginal. Now you might think of an array of those, but then you have to phase them and all that.
Yeah, that's what I did. I used 2 of them, and I used a phasing harness for both of them, and they're about 4 feet apart. Okay.
Well, it's probably worth a try. I'm not sure how much power those Arrow antennas can handle, though. You'd have to be careful.
100 watts. If you don't, watts? Yeah, if you don't get the duplexer built in, they'll handle up to over 100. So.
Okay. All right. Well, the other thing too is perseverance. Remember, this isn't easy, and with a QRP station, it's much more difficult. One thing I like to think about is, you may have heard of Shannon's theorem for digital communications. There's a theoretical limit for digital communications, how much energy you have to receive to decide noiselessly whether it's a 1 or a 0. Okay, you can come up with a curve, and communication engineers are always trying to push as close as possible to that curve by using different modulation schemes like BPSK or 64 FSK, trying to get to that limit. Well, it turns out that's for noiseless communication. I think we're probably operating beyond Shannon's limit, because our communications don't work all the time. If you look at the transfer curve or the error curve, the message error curve for JT65B, we're way down, like 50%, 10% successful message transmission. And that's beyond. Communication engineers don't work that way. You wouldn't want your phone to work that way. Ham radio guys work at the limit, sometimes beyond the Shannon limit, where you have noiseless digital communications. We're in a region where it barely works sometimes. So it's worth trying, but remember, you got to keep on trying, and there are going to be days when the ionosphere doesn't let you do it at all. There's one day I got 3 QSOs in one day, one right after the other. So it can happen that things line up and work well, but you need perseverance.
Okay. There's no more other questions, and I really don't have anything other than, I've been looking at some different antennas. The M2 makes some really nice dual polarization antennas. So
yeah,
but they're not cheap.
Right.
So, and
there's also the option you could potentially transmit on circular even at 2 meters, but it's not like, well, you could do it, and the guys with the big stations would reconstruct the signal so that they don't lose anything. They can add the 2 orthogonal polarizations as vectors to get a sum that represents the entire signal, with the other losses associated with it, of course, but eliminating polarization loss.
Yep. All right. Not seeing anything else.
Okay.
Also, what Eric said also is we could move this down to the roundtable lounges if we wanted to continue the discussion beyond here. So if anybody
Okay.
would, we'll all just go to the roundtable, and we should be able to find an empty table, and we'll all meet there and talk some more about this.
Okay. All right. We'll see you there.
Okay. See you later.
Yep.